Okay. Hello, everyone, and thank you for coming. My name is Eyal Shenitsky, and I'm software engineer at Red Hat on the oVirt storage team.
Hi, I'm Daniel Erez, an engineer at Red Hat and a contributor of oVirt project.
Okay, so thank you for coming, and today we're going to talk about Back to the Future, how we can do an incremental backup using oVirt. So, the agenda for our time journey today, we'll start reviewing the old supported backup APIs in oVirt. Then we'll see the new supported incremental backup API. Then we'll dive into the DeLorean hood and see how it works underneath. And we will show how to use it using the engine and Image.io backup API. So let's start. So how many of you used oVirt or know about oVirt? Can you please raise your hands? Okay, to see most of you, which is fine. Great, thank you. So this is oVirt from 10,000 meters above. We decided to show here only the main components that related to backup. So we have the engine, which is the management application, the Java application. And underneath it, we have the hypervisor, the host that runs virtual machines. And of course, we have the virtual machines disk. Also, we have an external application, a backup application that is an external application for oVirt and wants to back up those VMs, especially the disks. So how it can be done? So the old supported backup APIs, let's review them. We go back in time. The oldest solution is the backup appliance. The year is 2014, even before I was born. The backup applications runs actually inside a proxy VM. How it's going to be, the flow will be to take a VM snapshot, and then you will attach that specific snapshot to a backup VM. Once you attach the snapshot to a backup VM, inside that proxy or backup VM, you will copy the entire disk and detach, when you are done, the disk snapshot from the backup VM and remove the snapshot. Fine, let's move forward in time. We have a newer way. We have the image transfer API. If some of you were in the BearOS presentation, they're using this as their backup solution. So the year is 2017. You can now download and upload snapshot using the Image.io REST API. Image.io is a sub-project in oVirt to communicate with the engine and download and upload disks from oVirt engine to your environment. And it was presented since oVirt 4.0. So how the flow is going to look like? You just, of course, need to take a snapshot. When the snapshot is ready, you will download the snapshot as a QCode disk. Once you're done, you can remove the oldest snapshot. So in order to restore the backup that you've taken, you can prepare the disk for restore. It will be in the backup application. For example, if you have a chain of snapshots, you will rebase all those snapshots one on top of another, or any kind of preparation you need to do. Once you're done, you can upload the disk or the chain of snapshots using RAW or QCode2 format and create a VM from the uploaded disk. So those was the supported backup APIs. So now Daniel will present to you about the new incremental backup API.
Okay, let's see the incremental backup API. So, fasten your seatbelts. We're going to jump to the future. Okay, so the year is next year. We are still working on it. It's not done yet. So it will be in tech preview in oVirt 4.4. It will require upstream libvirt and QEMU 4.2, and the IT is incremental backup via change block tracking and using the NBT protocol. So let's see the full backup flow in a very high level. First, we start the backup. We have a simple API for that. Second, download the disks in RAW format. We don't care about the source format. We get it in RAW. And last, stop the backup. And there is no step 4. Simple API, simple flow. oVirt does all the heavy lifting behind the hood. Actually, libvirt and QEMU does the heavy lifting, but oVirt manages all of it. Okay, let's go for the incremental backup flow. Very similar. First, we start the incremental backup. Second, download the change blocks, again in RAW format. We don't care about the source. And third step, stop the backup. So again, very simple. Now, let's see how do we restore from an incremental backup flow. First, we need to prepare the disk for restore. The backup application needs to create a single file in RAW format. Then we upload the disk again, and then simply attach the disk to the new VM, and we can use the VM as it was before. Now, let's see the advantages of incremental backup. We have quite a few of them. First, copy changed blocks. And this speed up incremental backup, or actually enables incremental backup by copying only the changed blocks, since the less backup. Next, extends API. For full backup, we have a new extends API for exposing data extents and zero extents, so we can skip the zero extent and download only the data extents. Next, we are snapshot free now. No need to create or delete a snapshot, so all the complex operation of managing a snapshot, which can be quite complex as we know, no need for it anymore. And next, raw guest data. We can download the data in raw format as the guest sees it. We can convert it later if we want, but raw is supporting streaming easily, so this is more efficient. And then last but not least, we have an improved image.io client, which is a library that enables us to upload, download disks in both formats, even including the backing files. Now, let's see the limitations. First, with supporting only QCOW disks, we need the features of QCOW to get the extents. Next, it's available only for running VMs now. We can support it later on for non-running VMs, but this is current limitation. And last, the extents API is not useful for raw pre-allocated disks, as since for raw disk we get only a single extent, so we can't really do incremental. Now Eyal will show us under the hood.
Okay, great. Thank you, Daniel. So we saw how the incremental backup is going to work in the higher level side. So let's dive into the DeLorean hood and see how oVirt and QEMU actually doing those operations. So in the base of incremental backup, we have checkpoints. You can imagine a checkpoint like a lightweight snapshot. When the user is selected to create a backup, a checkpoint is created in the oVirt layer. Actually, checkpoints tracks the metadata inside this specific backup. For example, you can see here that the user created a backup in January 1st, and this checkpoint was created for that backup. You can see the backup that this checkpoint belongs to, and which disks are participated in the specific backup. So time moves forward. This is the first backup in the chain. The user in the day after selects to create a new checkpoint. So now a new backup and a new checkpoint was created underneath it. And now this checkpoint has a parent, which is the first checkpoint. And same disks participate in the specific backup. Fine. The day after, the user selected to create another backup, and another checkpoint was created, and now we have a chain. The chain of checkpoints will be persisted on the host as long as the VM is alive. In case the VM goes down or crashes or something happens to him, we need to redefine those checkpoints because oVirt is not aware of them. So we persist all this information in the engine database. So when the VM will rise again, engine will redefine those checkpoints, and the VM will be aware of what happened. So we have checkpoints. We know how it works in oVirt side, but checkpoints actually just track the metadata. What actually gives us the ability to know the difference between the bits that changes. So this is done by dirty bitmaps. As we said earlier, for each backup, we are creating a checkpoint in oVirt. And also, for each checkpoint, we are creating a dirty bitmaps on the QEMU level. So as you can see here, we have a disk SDA, and the user creates a backup. Also, oVirt creates a checkpoint for that backup, and a dirty bitmap was created for the disk. Each entry in the bitmap it marks a specific cluster in the disk. In the example here, we can see that the disk is clean. No data was written by the guest, so the bitmap is also clean. No bits got turned on, and no changes was made from the guests. So times move on. Guest writes data to the second cluster. So the second bit inside the dirty bitmaps turned on and marks us that this cluster is now dirty. Okay, the guest writes data to it. Let's move forward. The guest writes data to the fourth and the fifth cluster. we can see that even though that the first cluster is not fully changed, we are still mark it as dirty on the dirty bitmaps. Fine, so the user selected to create a new backup, so a new checkpoint was created and a new bitmap was created in QEMU, a dirty bitmap. The first bitmap of the first checkpoint is now deactivated, and we can see here that no changes was made to the disk, so the checkpoint, the dirty bitmap of the checkpoint is still clean. Once the user will want to download the backup in that stage, he will get the data that was traced from the first checkpoint. Okay, so now QEMU can report us on a specific disk cluster that got dirty. So if we want, we can get a map of the disk, of the extents, and we can see that QEMU will report us which extents got dirty or which cluster. So the first extent will mark us that the first cluster isn't got dirty, so the dirty will be false. And the second cluster got dirty, so QEMU tells us that dirty will be true. So we know this is the section that we need to actually download. So we know how it works. Let's see how we can use it using the Overt Backup API. The example here using the Python SDK that is layered on top of the REST API of Overt. In order to start a full backup, you just need to fetch the VM service using the Python SDK. And inside the specific VM service, we have the backup service. You just need to create a new backup using the add method and specify the specific disks that's going to be included inside that backup. Once we've done that, we get a backup object. We will wait for the status of the backup to be ready. Once the backup is ready, we can move on. And if you remember, for each backup, checkpoint was created underneath it in oVirt. So we need to fetch this specific checkpoint ID in order to provide it later when we are doing an incremental backup, in order to so the engine will know since when we are tracking the difference. So we fetch the backup ID, the checkpoint ID from the backup, and we can start a transfer session with image.io. So we are creating a new transfer using the image transfer, and we specify the specific disk that we want to download, and of course the direction of the download. Since this disk is part of a backup, we need to specify which specific backup it is, and the format must be raw. Okay, once we initiated the transfer, we wait for the transfer session to be ready, and when the transfer is ready, we can fetch the transfer URL. This URL gives you the direction specific to the host, to the daemon, so that the transfer and the download will be more efficient, and you can download actually the backup disk. Daniel will elaborate it more about this later on. So we have the backup, the full backup in our backup application. We can finalize the transfer and finalize the backup session. Fine, so we have a full backup. We can do an incremental one, right? But before that, we need to filter the disks. Only QCOW2 disks are supported for incremental backup, and the user must mark the specific disk that he wants to participate in an incremental backup. So this will be marked by disk backup.incremental. So we filter the disk that supports an incremental backup that we want to download, that we want to backup, and we can start a new backup, but now it will be an incremental backup. Okay, so we provide the disks that we filtered before, and we provide the from checkpoint ID that we fetched from the full backup that we done earlier. And the same goes on again. So now Daniel will show you how you can interact with image.io backup API in order to download the backup disk.
Okay, thanks, Eyal. So how do you download the disk? We can simply download the entire data, but it's not very efficient. We need to find a better solution, and we have one. So how do we do this? First, we send the options request to the server daemon on an actual resource, and we get an example response. We see that this resource supports the Extents API, 0, Flash. We can optimize the connection with Unix socket, and if we want, use multiple connections. Now, let's say we want to download 100 gigabytes image. How many gigabytes are in 100? Well, we don't really know. It can contain much zeros. But we don't really care about the zeros, so we don't need to download them. So how do we do it? first we get the 0 extents with a GET request, again, on the resource, and simply specify context 0. Now, an example for a response, we can see that the first request is 0, so we don't need to download it, we can simply skip it. And the second one isn't 0, so we shouldn't skip it. Now, which blocks change since the last backup for incremental backup? We can tell it by getting the dirty extents. So, for getting the dirty extents, we send a GET request to the resource, again extents, just now with context dirty. This is for incremental. So, this example, we can see that the first extent is dirty. So we should backup it, download it, and then the second one isn't dirty, so we shouldn't download it. So, getting the data. How do we get the data extents? We use HTTP range request. Again, invoke a GET request on the resource and specify a range header with offset and length. Okay, so now how do we speed up the restore? Can we speed up? We simply upload only the data extents. How do we do it? We send a put request on the resource and specify content range, offset, length, and size. And we simply need to send single request for each extents. Okay, now for the zeros. What about the zeros extents? We can use the 0 feature to zero the extents on storage. So how do we do it? We send a page request on the resource with operation 0, specify offset and size, and that's it. So finally, flashing is my data is really on storage. Well, we don't know. We need to flash it first to ensure it. This will, under the hood, invoke fsync command. So how do we do it? Send a page request on the resource with operation flash. It will invoke the fsync command under the hood. And this is done synchronously. Okay, was all of that too complicated? Well, probably, but luckily we have a much better solution. The client library. So what's the cool kids are doing these days? Apparently building overboards and using our amazing client library. So what is the ImageIO client library? It's basically a way to write your own time machine, easy. It can be a reference implementation for using ImageIO REST API. You can build your own backup solution, and it's good for testing your backup APIs. We have lots of examples of it in the code base, in the Python SDK. Okay, let's see the pipeline. You basically interact with the client, the ImageIO client. So for the for upload, the ImageIO client reads the data extents using QMNBD from the disk, sends the extents to the ImageIO daemon, which stores it in this destination. Again, QMNBD. For download, is simply the other way around. The ImageIO daemon reads data from the source to the QMNBD, sends it to the client, and stores it in the destination. So we have QMNBD all the way. Okay, so let's see how to do full backup with the client. We invoke the download API, specify the transfer URL and the name of the file. Here it's the default is a QCAR format, just because it's more efficient. Okay, so for incremental backup, we just need to specify incremental equals true, and that's it. Okay, how do we prepare the disk for restore? We need to rebase the images one on top of the other to have a single image to upload. So we incrementally rebased it up the last full backup. Okay, how do we use the client? We invoke the upload API, again with the image that we've created and the transfer URL. Okay, do you have some time for a demo?
Yes, okay, so thank you. We can see a short demo for how we can do a full backup. using the Python SDK and using the client library. So in the example here, we have one VM, a Fedora 30 VM. For the beginning, we just mark the disk as enable incremental backup, so we can use it for backup. We open a console just to create a directory that will illustrate that this directory will be when we downloaded the disk. After the backup will start, we create another one, and we will see that the other is not will be in the downloaded disk. We are using the Python script that we prepare for you as an example, and we are starting a full backup for the specific VM ID. The backup was started. We open a console again to create a new directory. That directory, the after directory, will not be included in the downloaded disk because it was created after the backup was started. So we created the backup. It was ready. We can create and start an image transfer. The transfer session is ready now. So we can start downloading the disk. This is the URL of the transfer that goes directly to the daemon. And the image will be stored in the following path that we provided using one of the arguments to the script. The backup disk was downloaded. The backup was successfully done. You can see here we have the disk. We're just creating another QCOW layer on top of it in order to not destroy the data. And we can start QEMU on top of it. So we have Fedora 30 VM. We log in. And we can see that we have only the first directory, not the second one that was created during the backup. Okay, great. So that was it. For more information, you have the following links here for the image.io and also image.io client, the SDK example, incremental backup feature page in oVirt and in QEMU, and of course for the oVirt site. If you want to investigate about it more, you can visit here. Thank you. So we have a little bit time for questions, if you have. Yes?
When I start the backup process, still I think the QEMU guest agent will still be triggered to enable to run some before script to stop a database or something like that to make certain backups consistent.
Yeah, the question was when we start the backup process, does QEMU run some backup sweep or something to QEMU guest agent? Yes. So we need QEMU guest agent, but we also freeze the VM on our side using the hypervisor, the VDSM. So we'll make sure that the data will be consistent and no harm will be made. And of course, when the backup is done, we are just the backup operation, which is quite short. More questions? Okay, fine. I guess that's it. Thank you very much.